lecture for M&E 490 on finite wing aerodynamics. This supplements what you should have read in your Anderson book and the other YouTube links that I placed online. First, we'll start out just by reviewing the 3D wing anatomy. This wing on this page is flying to the left, as we do by convention. The key geometric parameters are the wing area S, which is what we call the planform area. That's the surface, that's essentially the projected area of the wing. So it is not the same as the surface area of the wing, which would include both sides. This is the planform area S. This is used to normalize all the subsequent lift and drag coefficients, and this is true even in the case of the entire airplane. This is the reference area, the planform area. If it's a rectangular wing, that planform area is the chord of the wing times the span of the wing. Span of the wing, again, is this tip-to-tip distance. So when you think of the wing, it's one long structure, even if it passes through the fuselage, even if it's a mid-wing. The other key parameter, so we have the chord. The chord will vary in particular on any given wing, except for rectangular wings. This is the chord at the tip. We've heard it as the tip chord. The chord at the root, which may be inside an imaginary fuselage, which I would draw here. This chord here is the root chord, and the average of those, the average chord along the span is the mean chord. In the case of a constantly tapered wing, such as this one, we have the taper ratio is the ratio of the tip chord divided by the ratio of the root chord here. That's the taper ratio. A taper ratio of 1 is a rectangular wing. It doesn't taper. Some wings are tapered. If it's constant taper, the mean chord is just the average of the root and the wingtip chords. That mean chord we might use, for example, for a Reynolds number calculation to represent an average foil along the span. The moment coefficient needs an additional length scale. We use the mean chord for that length scale. So again, these are the lift, drag, and moment coefficients for the 3D wing. You have your dynamic pressure, 1/2 rho u infinity squared. This is the free stream velocity, and you have your reference area, which is the planform area of the wing. The other key metric, which will come up a lot when we're looking at 3D wings and how well they function, is the aspect ratio. Here defined as the span squared divided by the planform area. If it's a rectangular wing, this is just simply B over C, where C is the chord. It's any aspect ratio is a ratio of two length scales. Here essentially how wide it is. So it's a ratio essentially of this dimension to this dimension. So sort of how skinny the wing is. The key 3D effect comes from trailing from the tip vortices. So we have a wing here. We'll see that vorticity is generated all along the wing, but let's just think of it in simple terms at the moment. We have a higher pressure on the bottom than the lower, so think of any section of the wing here. We've already discussed the nature of that in class. What happens as you go toward the tip is you have a point where the lower surface and upper surface come together, and we can't have a discontinuity in pressure other than through a shock wave, and we're speaking about subsonic flow at this point. When these come together, they must be the same. And so essentially you have a pressure gradient between the upper and lower surface. This drives a flow in this sense. So this plane, we're looking at the front view of the wing coming at us, for example. It will drive a flow from higher to lower pressure. Flows like to move in the direction of lower pressure. And the result of that is associated with these wingtip vortices that look like this. I posted a video online that a friend had sent me that showed lots of wonderful images and videos of wingtip vortices from actual airplanes, planes visualized using either condensation created by the low pressure in these vortices, or actually flying through clouds, and you see essentially real flow visualization. These wingtip vortices occur, and we're going to see what the velocity field associated with these vortices is going to modify for any section on the wing where we've already discussed what happens as the flow comes over it. The flow that wing is going to see is different now due to the three-dimensional effects, namely these wingtip vortices. So here's a couple of snapshots you can clearly see here. So this would be connected to wingtip vortices that travel all the way back from the tips here, and essentially they are generated by the entire wing, but they roll up so that the dominant forcing comes off the wings here. And this one's oriented this way, and this one's oriented this way. So it's a nearer plane downstream, and this is just flowing through the clouds. And so you're just seeing a visualization of that velocity field induced by the lift in the clouds. Now this plane is landing or taking off. The flaps are way back, so I'm guessing it's landing, its gears down, and so it's in a very high lift situation. High lift means lots of wingtip vortex creation. If no lift, we don't have any at all. Some other any lifting configuration is going to produce this, as long as it's three-dimensional. And here we just have a keel of a sailboat, and this sailboat keel generates side force, hydrodynamic side force, to counteract the side force generated on the sails. And this lead bulb holds the ballast to counteract the moment of the side force on the sails to keep the boat from tipping. But you see spinning off the bulb here is a wingtip vortex, and this is the upstream flow is clean. The downstream flow downstream of that bulb has a significant roll up of that vortex. And here, actually, this is another sailboat shot, but in here it's very hard to see. This is a very low level fog, essentially fog or ground clouds. There's sailboats sailing through them, and you can actually see these streaks, very beautiful picture, streaks in the fog generated by the wingtip vortices. What does the velocity field look like? This is a slice through the wings. So we're looking at the wings coming at us again. And so this is a slice on the plane. This is a vertical plane we've been calling the Z coordinate, and this is your Y coordinate, Y direction here. So this is a constant X slice right through the middle of the wing. And this is the velocity field in that plane. Now the velocity field in that plane, these vectors are quite weak compared to the axial vectors, the ones moving past the plane. But when we examine in this plane, we can clearly visualize the flow field that's happening there. And you can see the flow is moving. This is from the simulation, but the flow is moving in that plane from the bottom of the from the bottom of the wing to the top of the wing. Now what the key thing is, the top of the wing here is experiencing this downward velocity. The whole top of the wing is experiencing a downward velocity associated with this wingtip activity. Again, this downward velocity is very small compared to the free stream velocity, but it's an important component nonetheless. It will have an effect on the flow field, and we call that downwash. The bottom of the wing is experiencing, or the outboard section of the wing, I should say, is experiencing upwash here. And that's a key component, particularly if you were to put winglets on this thing. So winglet like that. So this winglet is lying in this velocity field along with the axial velocity field, but it's also in this plane. And so parts of this winglet are experiencing very different velocities, as you can see here. Or I'll add a little red winglet on this side. So this, the nature of this outboard flow is also critical, particularly if you're dealing with a winglet design. I do want to mention here that this idea of vortices and lift and all this thing, everything is one giant coupled problem. So you can't just throw vortices into that flow field and have them react to that flow field. They will modify that flow field. So just saying we've added vorticity or this vortex to the 2D problem is not exactly correct. It's one giant coupled velocity field that satisfies the equation. So we're talking a little loosely when we talk about these sort of added effects of these adding on these vortices. There are some theorems that tell us that the vorticity can't be created or destroyed. So we have this bound vortex. Essentially, inside the wing lives a kind of vorticity. As the flow over it is more rapid than the flow under it, and so we have a vorticity here, and it passes. So there's one vortex filament we can think passes to infinity, or we can think of it actually passes to what we call a starting vortex that's still sitting at the airport, more or less. So when lift begins, we shed a starting vortex, and from there we have one continuous filament that goes up, it's bound inside the wing, and it goes back. This is sort of a very simple way of looking at it, again, as a single filament. To really look at this realistically, we have to consider an infinite number of filaments of different strengths depending upon the lift distribution along the wing. And we'll look at a snapshot of that later. And that's really the basis of Prandtl's lifting line theory for inviscid flow. Let me erase this because I do want to focus on this. Is a really important figure right here, and it's also discussed in your book, and it's discussed in that YouTube lecture I mentioned. This is really it when it comes to the mechanics of three-dimensional flow. Why is three-dimensional flow different than 2D? Why can't we just take a 2D wing section? This is how it behaves. Just extrapolate that over a full 3D wing and you're done. The reason comes down to this. I want to remind you again that there is a downwash associated with these wingtip vortices. You're on the top surface of the wing. There's a vertical component you would not experience if you were a purely 2D or infinite wing, an infinite span wing, or a purely 2D wing, or a wing that spans the entire wind tunnel from end to end, or side to side I should say, will not experience this particular downforce. This is because of end effects. End effects, we have a little W velocity. You can see it sitting here. It's going to come into the problem in a second. This wing's flying from right to left, excuse me, and this is the free stream velocity far away, this V infinity. It's parallel with the horizontal axis of this plot. And so originally we have this, the wing is at this geometric, what we call geometric angle of attack alpha. It's the same as the 2D angle of attack we've been talking about. This 2D angle of attack, or geometric angle of attack. This is physically how it's slanted, we could say, relative to the horizon, relative to the free stream angle. So in 2D, without any vertical effects, that would also be the angle of attack of the wing, that we go to our lift curve slope, look up our lift coefficient, and you're done. Now what happens is, because of this downwash on the wing, there's a small but active vertical component. Here it's labeled minus W because it's negative and it's down. And so what that will tend to do is take us from what I will draw as a blue curve, which is the free stream velocity vector, and it will cant that local velocity down to this green vector right here. Locally, this little piece of foil, which might reside right here, experiences a different velocity field, very close to the foil. Because it has free stream coming at it, but also has a component of vertical coming down, it tends to tilt down the velocity vector, such that the angle of attack that it actually sees relative to the flow field, here I've circled in green, called alpha effective, is smaller than the geometric angle of attack. We've reduced the effective angle of attack that the foil sees because of this downwash. So already this little section is flying technically at a lower angle of attack. The geometric angle of attack is still the same. The fluid angle of attack, or effective angle of attack, is smaller than that geometric angle of attack because of the downwash. So we've lost some angle of attack. The other thing that's happened is we've added drag. Now remember that lift is by definition normal to the free stream direction. But here we have a local free stream direction, or local velocity direction, which is tilted down. Here it is, this green vector right here. And so normal to, in a 2D foil, normal to free stream, which is parallel to this page, the flow of this page, is straight up. Now the velocity is coming at the foil along this green vector right here, and normal to that is tilted back. I'll just exaggerate a little bit. You can see these two black vectors which we have here. So what that means is that the lift force generated by this little section has a component that's in the direction counter to the direction of travel of this foil. The foil is moving this way. If the free stream direction were exactly this way, then the lift force would be exactly normal to that free stream direction and produce no drag, no component in the direction or counter to the direction of travel. With this case where we have a downwash velocity, our effective angle of attack is reduced, and now normal to that effective velocity, incoming velocity, or we say relative velocity, is normal to that is tilted back relative to the lift vector. So let me just exaggerate this. Here's the true lift vector relative to the free stream flow at infinity, far ahead of the foil. A reference velocity is not the same angle, and its normal is tilted back. It's tilted back, so that would be a big tilt there. The amount of tilt depends on the relationship of W and U infinity, because that angle of tilt which we call the induced angle of attack, depends on those quantities, and we'll look at the math on that in a couple of slides. So just think, very important, think qualitatively about this. It's a little puzzling at first, but it's very important that the presence of this downwash tilts back the lift vector, creating a drag component that would not exist in purely 2D. So a 2D inviscid wing, provided it's subsonic, so we're talking no shocks, inviscid, will experience zero drag if it's truly inviscid. A 2D inviscid wing will experience zero drag. Now, but a 3D inviscid wing can experience drag if it's producing lift, because there's a induced drag associated with that production of lift. Lift generates vorticity, vorticity generates downwash, downwash changes the relative flow direction for this little foil, tilting the lift vector back. It's tilted back such that there's a component of lift in against the direction of travel of this foil. That's a drag. We call that the induced drag because it's induced by the action of lift. So again, D'Alembert's paradox isn't valid anymore because we can generate in inviscid flow a drag. And so you have this geometric angle of attack, which is foil geometry relative to the free stream direction velocity far upstream. We have an induced angle of attack right here, and that's how much we're shifting back the lift vector. That induced angle of attack is the arc sine of W over V infinity. We'll look at the math for that in a second. If W is 0, if there's no downwash, alpha I is 0, alpha effective is equal to alpha geometric, and our induced drag is 0. Both lift curves are on top of each other. The larger W gets relative to V infinity, the larger the induced angle of attack is, the smaller the effective angle of attack is for a given geometric angle of attack, the larger the induced drag is, or the more that lift vector tilts back, and the larger component you now have is a drag rather than a lift on the wing. So it's really critical to make sure you understand all that stuff. It's purely qualitative, but it's very important. Prandtl's lifting line theory, essentially he placed a bound vortex. In the most simplest sense, you can think of a bound vortex living in this wing. And that bound vortex induces a velocity onto that wing, and it lives within inside the wing. And this single bound vortex, a vortex essentially induces a velocity field that is strongest near the vortex and decreases with distance. I'll try to draw it. Decreases with distance from that vortex. And so what this single bound vortex would do would induce a strong downwash here, and a weaker one here, and a weaker one that would go towards 0, and a strong one here, and a weaker one here, and a weaker one here, and a weaker one here. Now we know that's not what happens, and in reality what happens is vorticity is associated with the production of lift. And so in reality we have to think of an infinite number of bound vortices coming off of this wing. The strength of each of these, so you can think of these, it's hard to think about, but we have this is a wing. We're bound inside this wing, and we have one big vortex on the outside, and then the next one in goes up across the center line of the wing, down, and becomes this pair right here, and I'll just do the interior vortex right here. So we have 4, these are actually 4 vortices, another purple, that look something like this. And what Prandtl's lifting line theory does is allows you, and you can code this in a fairly simple manner, to take a wing, and this wing will have different sections in it. So it might be, say, a NACA 2412 foil here, and one with a smaller chord here, or maybe you're changing your foil as you go along, or maybe you're twisting your wing as you're going along, but all of these things will generate a certain lift distribution along the wing. You can vary the lift distribution by changing the chord, changing the foil, or twisting the wing so that the outboard sections are maybe at a higher or lower angle of attack, geometrically speaking, relative to the inboard sections. You can play with all these kind of things, and that will modify the lift distribution and vary the strength of these vortices back here. Maybe you're pushing the vortex strength on the outbound side, you're increasing it, and then decreasing on the inbound side, etc. So it depends on that distribution. These vortices together are associated with this lift distribution. So associated with this lift distribution here, and here I've drawn, this is a wing, and it pretend you're looking at from in front, and the wing's flying at you. It's this purple wing right here. This is a lift distribution, such that most of the lift is occurring at the midpoint of the plane. So I might put the propeller, is right here, is coming at you. The midpoint of the plane, or where the root chord is, and then we have lift going to 0. By definition, lift will go to 0 at the wing tips because we can't have a pressure differential in space. So the lift must go to 0 at the edges. But associated with that lift distribution will be some distribution of vorticity behind the wing, or in this bound vorticity model, that then we can deduce from that distribution of vorticity, or little vortices, distributed across the back. Each of them induces some kind of downwash, and we add that all up, and we get to some kind of downwash model. Here we see the downwash, which is coded by the yellow, a little stronger in the outboard side, a little weaker on the inboard side, but fairly consistent all the way across. We call that a downwash distribution. But again, this is a fully coupled problem. If you mess with, say, the foil section right here, let's just say you make it a little bigger or put it at a higher angle of attack, now that's going to affect the entire problem, because that will modify locally the section lift, which will change the entire lift distribution, which will change the induced velocity associated with that lift distribution, which will change the downwash distribution. And now the downwash distribution changes, which changes the effective angle of attack of the entire wing. So again, that will change the lift distribution everywhere. Everything's tightly coupled. It's effectively an implicit problem. We can't make one adjustment in one spot and say, oh, this is what's going to happen, because it will affect everything else, which affects everything else, in an implicit manner. Prandtl's method. So that's the key thing, is by twisting the wing, by changing the chord of the wing, by changing the foil that we use of the wing, it will modify the lift distribution, which changes the ultimately this downwash distribution. And so these are these two things that you can do here. You can mess with the chord, how the chord varies along the span. For example, a rectangular wing, this is viewed from above, the chord might be constant. Or you might use, for example, a tapered wing, which we'll be using in our homework foils. That one wasn't very tapered very well. So the wing tips are smaller than the inboard wing. But maybe in these simple wings you want to use the same sections and don't twist them. That would certainly keep construction costs down. Or you could use a rectangular wing and start to twist it. And that will mess with the lift distribution. So there's different ways to do it, and it really comes down to optimizing structural constraints and in particular cost. If we're talking about recreational aircraft, having a single foil across the entire wing, just scaling it down is certainly cheaper than messing with the foil shape. Twisting a wing makes it more difficult structurally. I mean, how do you deal with the spars and connect these twisted sections together? Once you start twisting it, it's going to add some significant expense. So economics really plays a role in this. Ideally, what you have, assuming the inflow is uniform, which is fine for an aircraft, not so fine for things like a sailboat sail. Assuming the inflow is uniform, you have an elliptic lift distribution is optimal. And what that means is we look at the distribution of lift along the wing, it is elliptical in shape. Can be characterized by equation for an ellipse, where you have the major axis, and this is half your minor axis in this direction. It's, again, peaking here, goes to 0 at the tips, but the shape is an ellipse. An elliptical lift distribution could be produced by an elliptical planform, but it doesn't have to be. We could also almost exactly produce it by twisting, by messing with twist and foil shape. We could do the same as doing an elliptical constant foil, no twist shape. There's different ways of getting this lift distribution. It doesn't mean the wing has to be elliptical in plan form, but it can be. This will produce constant downwash, and it turns out that constant downwash from an elliptical lift distribution produces constant downwash. Every section sees the same negative velocity. This wing will produce the minimum amount of induced drag possible. So this is the goal to get at, is to say if I want to lessen my 3D effects as much as possible, then I want to pick this particular lift distribution. So again, you can do this a number of different ways. The way it was done on these fighters here, like the Spitfire, and this Henkel here, this is a German aircraft, you could see that these are essentially ellipses. Now, think about the chord they have to make. You know, if they use a constant foil, they're essentially scaling that foil down. So the T over C, the foil shape stays the same, but the chord is decreasing, is going with the in the shape of ellipse. No twisting, no change to foil. Elliptical shape will produce an elliptical lift distribution on this foil, which produces constant downwash and minimum induced drag. So that's the idea. You can see that here on this this big roach on this sailboat as well. The effect of having to put all these battens and structure up here to keep this was approaching an elliptical lift distribution. Now, if you go to your average airport, you won't see any planes except for maybe some old restored fighters that look like this. Because for two reasons. One is that it's more expensive to do this, and the other is you can come pretty close to producing these ideal distributions by using a good smart taper ratio, also messing with twist and other factors that are cheaper perhaps than making a construction like this. Now, getting to some of the quantitative components. Again, we have our foil shape. Here is V infinity out here. But once we put our downwash in here, the local flow direction is on this line. It tilts. This foil sees flow from that direction rather than from this direction, which takes our original lift vector here and tilts it back because it's normal to that local flow direction. That tilt back means we've added an induced drag here. We can quantify that. First of all, the angle of the alpha I here, the induced angle of attack, right? That we don't want that. That's basically the decreased angle of attack that occurs because of this three-dimensional effect is given by the lift coefficient of the wing divided by pi, pi is pi, divided by the aspect ratio. So the aspect ratio will come into most of these formulas because we have to consider the case where as the aspect ratio goes to infinity, we're essentially recovering the idea of a 2D wing. So all these things should go to zero as the aspect ratio goes to infinity. We can see the induced angle of attack, for example, goes to zero as the aspect ratio goes to infinity. And we also will see, which also means that the bigger the aspect ratio, the smaller the 3D effects, the less detriment we have, the less induced drag we have, the less the associated angle of attack is decreased, etc. And this is a critical part of performance. Again, if you look at gliders, if you look at the U-2 airplane, they use extremely long wings because they're trying to keep drag as low as possible, the induced drag as low as possible. But you do run into structural issues as you get wings to be very long. So the main thing you're fighting really is structure. And that's a big part of it, cost structure. The induced drag is, so this, we're tilting the lift vector back by this induced angle of attack, alpha I. And if we, and sine of this angle is di, is the opposite edge of this angle here, and the lift vector is the hypotenuse. So we have sine alpha is di over L. So it tells us if we non-dimensionalize using them the same way, and we consider it to be a small angle, so we can sine alpha is equal to alpha, that's the small angle of approximation, non-dimensionalize both of them, we find out that the ratio of the induced drag to the lift coefficient is this induced angle of attack. Again, as the induced drag goes to zero, alpha I will go to zero. But since CL is thus alpha I times CDI, and alpha I is CL over pi AR, we find out that we can solve for these two things for CDI, or the induced drag coefficient, and find out, very importantly, it is proportional to the square of the lift. It's very sensitive to the lift. This tells us that, for example, on takeoff and landing, when your lift coefficient is going to be big, maybe 3-4 times what it is when you're at cruise, maybe more, you will find the induced drag is humongous compared to the friction, the parasitic drag, the profile drag. At cruise, it will be a much smaller fraction, and depending upon the type of airplane and what it's doing, will sort of determine that ratio. But it's quite sensitive to this lift coefficient. When you're in a high lift situation, induced drag is going to become prominent. And again, we can reduce that induced drag for a given lift coefficient by increasing the aspect ratio. If we have our little plane here, we can choose a wing that looks like this and one with the same surface area that looks like this. I don't know why you would want to do that. You can already feel like there's something wrong with that, but perhaps they can produce the same lift, but the induced drag on this one will be far smaller than the induced drag on this one. So that is the nature of the aspect ratio. Comes into all of these equations. And so that's the nature of drag. So again, the induced drag here is a very important formula to remember. We're going to augment it a little bit. This is for, specifically I should mention, for elliptically loaded wings. So this is an elliptic lift distribution. What we will do for cases when we don't have an elliptic lift distribution, for example, if we have a tapered wing or rectangular wing, is we're going to add a little parameter down here. We'll see it in a few slides, but it's just a slight modification to this formula rather than having to do any fancy new computations. Now, again, we also have a loss of lift. In particular, once you start tilting back, let me just go back one more time to the slide. Once you start tilting back this lift vector, right, you're essentially turning lift into drag, and you're losing lift at the same time. The angle of attack goes from your big geometric angle of attack, and now as the downwash comes in, it tilts back. If we have even more downwash, it will tilt back even more. And this is the actual angle of attack now you have to work with. So you're decreasing lift. At the same time, you're increasing drag. It's a bit of a double whammy. So we like to think of this, or aerodynamicists think of this in terms of effects on the lift curve slope. So the lift curve slope in 2D, and again, we go to your drag polars and lift alpha diagrams from your book. So we'll call this your CL alpha. Actually, Anderson likes to use the little CL versus alpha. And you see your polars and goes up in stall. Maybe the aerodynamic data looks something like this. And the slope of this line here is the lift curve slope. And if this is a foil section, say this is your 2412 foil, the slope of the linear portion we call A naught. That's the A naught over here. And we can write essentially a modification to that lift curve slope due to the three-dimensional effects. So here's our lift. Here it's given by our original 2D slope. Now we're subtracting out this alpha I, this induced angle of attack. Basically, the 3D effects are cutting down our angle of attack. So we're shifting this line down, but this induced angle of attack depends on CL. So this is going to vary with CL. The result is that we have another equation for the lift coefficient, which looks like this. So in 2D, we would say CL equals A naught, the lift curve slope, times alpha minus alpha naught, and where alpha naught is the angle of attack at zero lift. That's the equation for this line right here in the red portion until it starts stalling. This equation for this line right here. This equation is very similar. The only difference is the slope right out here, where we have A naught in the numerator. That's a 2D lift curve slope, but we have this term in the denominator, which is going to change the denominator to be something greater than 1, meaning the effective slope is going to be less than A naught. Again, you can see the aspect ratio having an effect here. And what this means is we'll get a decrease in the slope. Alpha naught is still the same. Once we get to zero lift, it doesn't matter if we're 3D or 2D, we have the same lift coefficient, which is 0. Alpha naught's the same. But for a given aspect ratio, this will produce a line that has less slope. And that slope is going to depend on the original A naught, and it's going to depend on the aspect ratio. If the original A naught, which depends on the foil in the wing, that's a fixed number, mess with the aspect ratio. So now we have an aspect ratio, say it's 10, and then we have an aspect ratio, say it's 8. All it's going to do is decrease this lift curve slope further and further. So this is decreasing aspect ratio. As aspect ratio goes to infinity, we should recover the original 2D line. And we look here, if we let aspect ratio go to infinity, that thing in the denominator is 0, and you just get A naught over 1. We get our original equation down here. So again, we recover the original 2D solution as the aspect ratio goes to 0. So again, infinity rather. So again, this is Prandtl's solution for thin finite wing. So we're not accounting for a lot of stuff, but it's quite accurate. Here we have the lift curve slope. Remember, in his case, A naught was equal to 2 pi. A naught is the slope for a real foil. For an infinitely thin foil, Prandtl's solution for a 2D wing, the lift curve slope was this magic 2 pi, which is not far off a typical foil. A thicker foil might be a little above this, but you know, talking about 10%. So here's, if you don't know the A naught for a particular foil, or you don't even know the foil section for your wing, you could use this formula, which would be pretty accurate, and you can still see the aspect ratio effects at play. And this is just for a thin infinite wing. We've already discussed that in the context of 2D aerodynamics. So this picture just basically recovers in a nicer way what I just tried to draw, where you have a lift curve slope for your 2D section. You put a section in a tunnel, it spans the entire tunnel. There are no 3D effects. You tilt it up, you measure the lift, you tilt it up, you measure the lift, eventually it starts to stall. You take your data and you go home. Now, what are the effects of aspect ratio? We can see them clearly here. Basically, they're changing the slope of this line. They're reducing the slope of this line as you lower the aspect ratio. So, for a given angle of attack, you're producing less lift at a low aspect ratio than the 2D case. And you can see as you get towards small alpha, the differences in CL, the delta CLs are small, but at high angle of attack, the delta CLs are quite significant. So those are two key things. You bring in induced drag, again, proportional to CL squared over pi, or it's CL squared over pi times the aspect ratio. We have induced drag proportional to the lift coefficient squared, and we have a loss of lift. Basically, the lift curve slope is reduced. Now let's think about other planforms. So again, these formulas are all for, these formulas, which are all a big mess now, but these are all for the case of an elliptic lift distribution. You can solve for this from Prandtl's theory as he did and come up with these beautiful, elegant formulas. Now, we won't usually see elliptic lift distributions. So what if we don't? How do we deal with a non-elliptic lift distribution? For example, we're going to mess around with this plane and also the 182, which shares a similar wing, in class. And you can see if you look carefully that what they did is they have a section that's rectangular and a section that's tapered off. And that's to basically produce something that's cheap to construct but also produces a nice close to elliptical lift distribution at a pretty low cost. So they sort of optimize this concept and use this on a number of aircraft. And they use a single foil section, the 2412, all the way across from the tip root chord, which is longer than the tip chord, but the same exact profile, same section. Here we have essentially constant taper ratio, constant taper wing, and you might see a lot of aircraft that look like this. Rather than using a section that's rectangular and then a tapered, basically two-section wing, here's just a wing where they're just cutting the chord down linearly all the way across. And so you could use similar sections in here, they're just getting smaller and they're tied together using the infrastructure of the wing. So this keeps costs down. And how do we bring in this this factor? Again, we have for example, our induced drag coefficient formula. What we're going to do is add this little factor right here we call E. Now E will be 1 in the case of an elliptical wing. That is the span efficiency factor. Sometimes you see it written in some books as the induced drag factor, and they are related in this manner right here. For example, what's plotted here is the induced drag factor, which you can convert to E in this manner. Induced drag factor 0 is good, span efficiency factor 1 is good. So 1 is the elliptical lift distribution, we cover that formula. But if we have a non-elliptical lift distribution, for example, if our wing is tapered and untwisted and uses a constant foil, it will be non-elliptical. Here, for example, our variation of taper ratio and aspect ratio. Now for the wing, we'll be working with in class. I think the aspect ratio is about 8 and the taper ratio is close to somewhere around here. So you would figure out what your taper ratio is. That's a geometric parameter. Your aspect ratio is a geometric parameter. You draw this over here and figure out what delta is. You pump it in here, and this is going to end up being about 0.98, something like that for E. So you can get to close to 98% efficiency compared to if you really went to the expense of making a wing that produced an elliptical lift distribution, which is quite extraordinary. So aspect ratios, you can see, is the induced drag and loss of lift are very strongly linked to aspect ratio. Aspect ratio is really important. The span efficiency factor is more, I would say, more of a bit of fine-tuning relative to messing with the aspect ratio. And with something that looks quite simple to construct, you can get pretty close to something that's considerably more complex to construct, simply by tapering it properly. And again, we modify our formula for the lift coefficient. So again, this is our augmented lift curve slope from the 2D case, 2D foil case A naught. We have this new term in the denominator, which will be non-zero in the case of a finite aspect ratio. And in there is our little e right here. So we'll augment the lift curve slope as well. So those are really the critical concepts of 3D. It's important that you understand how downwash occurs, and the downwash occurs in 3D, and that downwash distribution we want to be constant along the wing. And the effect of downwash is to decrease the apparent angle of attack. So we reduction of lift, and it shifts the lift back. So there's a component of lift relative to the local direction, which is in the drag direction. And what that will do is, what that is induced drag. So computing the induced drag, which depends on the square of the lift coefficient and is inversely proportional to aspect ratio, and computing the lift coefficient using the augmented lift curve slope, which is smaller than the 2D lift curve slope. And the lift curve slope is, the lower the aspect ratio, the smaller that is. There are ways of recovering some of this, or basically lessening some of the effects of induced drag, and there are different ways of looking at this, but essentially in the simplest way, you have a wing. If you put of a kind of end plate on there to reduce, now there's different ways of looking at this, but we can think of this as reducing the wingtip vorticity. But another way of looking at this is part of the wing, and it's experiencing this local velocity field, so there will be forces on these plates which may generate, in particular, a thrust. And that's some of the idea of these, is they're actually, the flow around this wing can induce a velocity on these that is a net thrust velocity. And we can think of that in the sense that we've reduced the induced drag because we have some parts of the wing pulling, and overall we should think of this as reducing the induced drag. A key trade-off, of course, is that we've added extra surface area, so we have to ensure that the additional frictional drag isn't killing this whole concept. So when you can add these to airfoils, wings. You see just about every commercial aircraft these days now has these, sometimes retrofitted on there. There's a couple different designs, a scimitar design and others. Here you see just a flat wing. These can also have control effects. If the wing starts to slip, if the plane starts to side slip, for example, it will induce velocities on these which will stabilize them. You'll see that this plane has no tail at all. So they've essentially taken out the tail effect. So if something jostles this plane left or right, it will induce a velocity on these which essentially will work against that jostling motion. And these become the vertical stabilizers. In other cases, and this is in particular dating back to the America's Cup in 1983, the first time the U.S. lost the Cup in the history of it, they were racing these 12-meter boats. The 12-meter boats had a fixed draft, basically how far the keel could stick below the water surface. And you want it to be long because you want a high aspect ratio, an efficient keel, but the rules say it can only be so long. And so one thing you can do is say, I'm fixed by the rule of the draft, but I can increase my effective aspect ratio by using end plates. In these cases, they also have other effects of holding lead. For example, ballast can be stored in here. And there's also additional important things when you're sailing at some sailing angles. For example, the wind's behind you, you don't really need to produce side force. And the boat's essentially moving forward without heeling. And these can do things like damp motion and waves and do other stuff. So it gets quite complicated in the sailboat world, but the point is that they show up in all forms of life. And there's a way of looking at, if you see birds' wings and they have those little feathers, particularly birds of prey. This is horribly drawn, but you look at a condor and they have these kind of little feathers at the end. There's a lot of analysis of these and the flow through these feathers and how the main structure of the wing interacts with these little wings. You could think of them as winglets, little tiny wings on the bird's wing. So often you see a hawk, they'll have those flight feathers at the end, which they can manipulate, of course. You can't manipulate a real wing. Just another note about finite wing effect. You see geese traveling in a V like this, and overall, if you sum up all the drags of these individual birds, if they were to fly far apart, it's greater than the whole. And so this bird, for example, here is inducing, has wingtip vortices associated with the lift he or she has to create, and if these guys, birds, are outboard of that, they will be on the upwash side of that vortex. If we put another plane right here, for example, and another plane right here, they'll always be on the upwash side, so the net drag compared to the individual parts can be less. So a group of birds can fly more efficiently in that particular formation. Who knows how they figure that one out. And this has important implications if you're landing behind another plane, because they're inducing, particularly in a high lift landing situation, very strong vorticity, and a small recreational aircraft that gets stuck behind this might have these vertical velocities become quite strong relative to the free stream velocity, because you're slowing down but you have high lift, and can, if it's affecting, for example, one wing and not the other wing of this aircraft, can lead to a moment like this and sort of a disastrous situation. That's why there are rules at airports about how close you can land planes together in order to avoid those kinds of engagements. So just a compact flow chart. You have a plane, ideally you have money, you go in the wind tunnel, you test the real 3D thing, and you kind of see what's going on. If you don't have that kind of money, then you can do a couple different things. You can go get your choose your foil shape, get your lift curve for those sections, choose your aspect ratio, figure out planform you're going to use, get your planform efficiency factor, and then start computing the necessary formulas. You can use either profile drag if you have that from the foil section, or you can use just simple flat plate drag formulas, maybe one that accounts for the thickness to chord ratio, to try to get an estimate of the profile drag of the wing. If you don't have anything, then you can go back to your 2 pi theory and make your best from there. And I just want to show one quick simulation. Hopefully this is still running. I'll try to pull this into my recording window. So this is an Onera M6. It's sort of a famous test case actually for transonic flow. Here I've slowed it down to Mach 3 for the simulation to make sort of incompressible limits. What you see here is pressure on the wing. So let me try to turn the wing around here. You'll see the pressure distribution on the wing. And let me get rid of the streamline for a second. Oops. Scroll out here. So the pressure distribution on the wing here, the lighting's a little funny, but I have it at a pretty high angle of attack. You can see the stagnation pressure right here on the bottom of the lower surface, and you have a strong suction peak right here. In fact, this angle of attack's close to stalling, but I ran invisibly, so it didn't stall on me. So the flow's accelerating over here, but I've run these streamlines through here, which you can see in this image right here. Essentially, you seed the flow upstream. This is steady flow, and it just integrates the velocity field back, and you have part of the some of the flow goes above, some of the flow goes below. You can see it separates, and you have this strong wrap-up of the vorticity, particularly at the wing field. So you see the vorticity rolling up, even rolling up here. These two streamlines go over, and they actually kind of crisscross. The streamlines come here, and they sort of spread out and separate, and then so they're not meeting at the exact same place on the trailing edge either, due to particularly the sweep of this wing is having a large effect. This swing is swept back to reduce the, well, we'll talk about that in class. For transonic flow, we sweep the wing. And so let me just turn on one other, just the wingtip vortex. You can see the same streamlines come back, and now they're rolling up. Now, this particular grid, well, it's a very simple grid. This is computed with SU2, the Stanford University Unstructured design code, and this is one of their test cases. So it's designed to run fast to make sure the code's working. It's not particularly well resolved. So if you really wanted to resolve the downstream here, you'd have to specifically refine your mesh in this region, even though you don't really need it for computing the forces on the foil. So the mesh is getting quite coarse out here because it wasn't necessary. So we lose the real interaction effects as these roll up. But the key thing is you can clearly see the roll up of the vorticity over this particular wing because it's producing lift. If I put this thing to 0 lift, you wouldn't see the roll up. You only see this due to that.